Hello, this is lecture 5, measures of possession and the box plot. What we are going to discuss today is measures of possessions, percentiles, quartiles, and then we are going to talk about the interquartile range, how to calculate it, outliers, and how to detect it using the box plot rule. And we are going to, of course, introduce the box plot. Measures of possessions. Percentiles. What are the percentiles? Percentiles, which we are going to use P subscript small p to represent it. These are 99 which are separating the data set into 100 equal groups. So imagine with me this line is representing our data. This is a line of numbers, and we're gonna put our data from the minimum value till the maximum, just listing them on this line. And then percentile are just separating the range of our data into exactly 100 equal group. Each group is gonna have underneath it 1%. So P1 is having 1% below it of my data. P2 is having this 1% plus this 1%, so it is having 2% of my data points below it. So P2 is the second percentile, P1 is the first percentile, and P3 and so on till we will have 99 percentile exactly, and these are separating the whole range into exactly 100 equal groups. And again, this little tiny number here, this is the percentile rank. So the percentile rank is what? This is P, that little tiny p, and it represents the percentage of data values below this specific data point. So all of these circled one are my percentile rank, and the percentile corresponding to a given data value x is computed as following. So if I have a specific value, we call it x, and I want to know that x is representing which percentile, or what is the rank of that x in terms of percentile, then I'm gonna use this rule, which is what? Which is saying go ahead and add and count how many observations are below that value x that you are interested in, add half to it, multiply it by 100, and divide over the total number of values in your data. So this is how to know the rank of a specific value in my data set. But what if you would like to find a specific P's percentile where you know exactly that P, you know exactly that rank now? What is the value among my data values that are representing or would be the P's percentile? To find that, I can go ahead and go through these steps. First, I'm gonna arrange my data, and then I'm gonna get what is known by L, standing for location, which is n times p over 100. This p is given again. And now that number, it's either a whole number or not a whole number. So if L wasn't a whole number, then you are gonna just round it up to the next whole number, and the P's percentile would be that value exactly in that L, which is representing location or position in the arranged data set you have at your hand. So this is if the location was again not a whole number, you're gonna round it up, and then that value in the arranged array of your data that is exactly in the value of that rounded up position would be the percentile you are searching for. On the other hand, if L was already a whole number, then we are gonna take the average of these two values that are in the else position and the following one, L plus 1 position. Average these two values will give you the percentile that is the base percentile you begin with. So let me see an example. These data represent the values in billions of dollars of the damage of 10 hurricanes, and we want to find the percentile rank of the hurricane damage that is associated with that specific value. Okay, so we want to find a percentile rank, which is that little tiny p that we did talk about. What is actually the rank of this one? Again, what was the rule? I'm gonna arrange first my data, and after that, so arranging it from the smallest to the highest one. So 1.1 is the smallest one, then the second smaller value is 1.7, and so on, arranging it till we are getting to the largest value. And then we're going to calculate or apply the rule for the rank P, which is the percentile rank, which is P, that little tiny b, is equal to how many numbers do you have below that specific x. But what is x? X is that one, 6.2, the value that is in your interest or in the question. So in my arranged value of my data, I want to know how many value came before that 6.2. So here is my 6.2. So I'm gonna count 1, 2, 3, 4, 5, 6, 7. So I have 7 values below 6.2. So that part would be 7. And I'm gonna add half to it, divide over the total number of the values. How many total number do we have? We have 10. And here it is written in our title, but even if it wasn't written, I can just go ahead and count these. It would be 10. So 7 smaller than 6.2 plus the half in the formula, dividing over how many data value you have, and multiply by 100. It gave us the 75. So this means this hurricane damage was higher, which is 6.2, was higher than 75% of these hurricanes, of these 10 hurricanes. Okay, and it is actually the 75th percentile. It represents the 75th percentile. So for the same data, we want to know the rank of the 40s. We want to know the 40th percentile. So we know now the rank is 40, but what is the value among my damages? In those 10 damages, we have what is that value that is representing the 40th percentile, or in other words, what is that value that is having 40% of my data value below it. So this is to find the percentiles itself. I know already the rank, so the rule was what? Again, we need to arrange and find the value that is in this position, which is L n times P over 100. N is again the 10 we have in our data values, and 100 is constant, and P is what? P is that rank, so P is 40. So 10 times 40 over 100, it is in the location 4. But we see it if the location was a whole number, then the percentile is the average of these values that are in the 4th and the following ones, so the 4th and the 5th position. I'm gonna average these values in my arranged data set or arranged array of my data set. I'm gonna average these, and this will represent the 40th percentile. So here are my arranged array of my data set. Again, we have seen that in our previous slide. And I'm gonna just go ahead and find what are the values that are in the fourth and fifth position, average these two. So 1, 2, 3, 4, this is the fourth and this is the fifth. So I'm gonna take the average of these two, and this will represent the 40th percentile. Now let's calculate the 95th percentile, or find the 95th percentile, or what is the value of my damage that corresponds to the 95th percentile. Again, this is the same idea as we had up here. I know the rank, which is 95. I need to know what is the value among my data points that is representing the P95. So we are going to use the same rule, which is the location, or L, or the possession. 10 times the rank, which is 95 here, over the 100 will give me 9.5, and this is not a whole number, so we need to round it up. Rounding it up, it's gonna give me 10. So in my arranged data set, what is that value that is in possession? 10. So actually we have only 10 values, so this is 95 percentile. I have 95% of my data below it. So our second topic here is quartile. What is the quartiles? Quartiles of a dataset divide the data into 4 parts, and each part is exactly of 25%. So again, imagine I'm gonna list all of my data on the line of numbers from the smallest one, the minimum one, to the highest one, and I'm gonna have exactly 3 quartiles, such that I'm gonna have exactly 4 parts of my data, where each part is representing exactly 25% of my data. So that one is a quartile, that line is a quartile, that line is another quartile. So to have quartiles, we have only 3 quartiles, such that we are going to end up with 4 equal groups, each one of 25% size. That one, the first one, is Q1, and it is at the same time the P25. We did discuss the percentiles. That point would be having underneath it 25%, so it's in the at the same time it is Q1 and the 25th percentile, while that one would have underneath it 25 and 25, so it is having underneath it or below it 50% of my data, and we did talk about that measure before. This is the median, and in terms of quartiles terminology, now it is the second quartile. So it is the median and the second quartile, and also the 50th percentile. While the last one, this is having underneath it 75% and above it only the 25%. So because it is having here 75%, this is the third percentile, and at the same time it is the 75th percentile. So it's the third quartile and the 75th percentile. So let's how to find quartiles. To find the quartiles, we need to follow the following rules. First, we are going to arrange our data, and then to find Q2, we are going to find the median of all of our data values, because the Q2 is nothing but the median, as we did say. So MG, the median, is equal to Q2, and at the same time this is equal to the 50th percentile. To find Q1, we are gonna get the median for the first half of our data, which is those values that are below Q2, lower than the Q2 values. And Q3 is similarly, this is the median for the second half of our data, those that fall above Q2 in terms of their values. And I could also use the rule for the percentiles, the L rule, the possession rule, to identify the position of Q2, Q1, and Q3 just because there is a relationship, a one-to-one corresponding between Q2 and one of the percentiles, the P50, and Q1 is the same like the 25th percentile, while Q3 is the 75th percentile. I can graphically use the ogive to read from the graph Q1, Q2, and Q3, and even any percentile could be read from the ogive, as we will see in our next slide. So here is an example of how to find the quartiles or any percentile if we would like from ogive. So this is a table that a frequency table that is representing the cumulative frequency in it and the relative cumulative frequency or the cumulative frequency percent. I do have 1, 2, 3, 4, 5, 6, 7 classes, but the first one is having cumulative frequency equal to 0. So this one is the class that we add just to let our ogive begin at the 0 point. So the original table of my frequency distribution for those SAT scores are having only 6 classes. 1, 2, 3, 4, 5, 6. How many SAT scores do we have? We can read that from our cumulative frequency column because we know that the last cumulative frequency is n. So we have 45 scores. And to graph our ogive, I could use the cumulative frequency or the relative cumulative frequency. Here, in my case, I use the relative cumulative frequency. So, at the 147.5, I have 0%. This is again the class that we did add to begin our ogive at the 0 point. And the second class, it's 13.3%. And how many frequencies are there? Below 157.5, this is my third category, and so on. So this is my ogive. To use the ogive to find the 50th percentile, which is the median, I'm gonna go at the position of 50 here on my y-axis, straight till I hit my curve and down. I'm gonna read from here the value, which is the median. So it's like it's maybe from my graph, it could be, I'm not that sure right now, but it could be like 159 or 160. And if I want to find, for example, that at 25th percentile Q1, I would go to my y-axis at exactly 25 value on relative frequency here, so 25%, 25, and I'm gonna go straight till I hit my curve, and down there from that point I would read from down here Q1. If I want to find maybe P, the 80th percentile, I would go to the 80 and straight till I hit my curve and down there, and I would read the 80th percentile from here. So I can use the ogives to read Q1, Q2 and any percentile, and also a Q3 from graphically from my ogive. So let we see another example where we would calculate our Q1, Q2, and Q3. So we have here 42 scores for biology test, and we want to go ahead and calculate Q1, Q2, and Q3, but just a note here, the professor for this class did offer students the score, those students who will score in the top 5% of the class extra credit. So let me see, those are my numbers. Okay, my 42 values of my test, biology test. So what is the score that is needed to receive the extra credit, those who are gonna be in the top 5%? Well, to be in the top 5%, then underneath them or underneath that score should be 95% of the scores. So actually it's like what is the question is translated to to, or could be translated to what is the 95th percentile, because to be in the top 5%, it means I will have underneath me, or my score will have underneath it 95% of the other scores. So we need to go ahead and use the location rule or the position rule, which is n times the rank, which is p over 100. So n was 42 for this example, and we are talking about the 95th percentile, so the rank is 95, which is a p over 100 would give me 39.9, and this is not a whole number, so we need to round it up 40. So that score that is in position 40 in the arranged array of my data would be that score that will enable me to get that extra credit. So let me go ahead and put the arranged data set. So this is the arranged array for my data set. We had the smallest value, minimum was 44, and the highest was 100, and this column is representing the position, or the L, so we need to go to L equal to 40 down that column. Here is my 40, so the value that is listed beside the 40 is 95, so this is my answer. This is the score that will enable me to get that extra credit. Now we have been asked here to find all the quartiles, the 3 quartiles. Again, it's easier to find the median, which is Q2, and then find Q1 and Q3. So for Q2, as we did discuss before, we need to find the median of my data set. I have 42 observation, and 42 is even, so 42 over 2 would give me what? It's gonna give me 21, and because I have an even, so the median would be the average of my two values exactly in the middle. The first one is n over 2, which is 21, and the following one. So those two values at the position 21 and 22 get the average, so 75 plus 76 over 2 would be my median. So the median is 75.5, which is Q2. And for the Q1, it is the median of my first half of my data. Those data that are below, in terms of their values, below the median. The median would be exactly in that middle, see, in between. So how many values do we have here? I have exactly 21 value. So this is odd. So the value exactly in the position, or in the middle of those 21, would be my median of my first half of my data, which is Q1 by definition. So 21 over 2, to find the middle, 21 over 2, it's what? It's 10 and a half. It's not an even number, so I'm gonna just round it up. So the value of my Q1 is the value in the position 11. So Q1 is 61. For the Q3, it is the median of my second half. So I began my data with 42 observations. So 21 here and 21 here. So again, I'm gonna just divide the 21, the bottom 21 over 2. It's gonna give me again 11. But because I began my numbering from the 22, so that 11 is actually gonna be the 32, or that value exactly in the middle. Forget about that column. Exactly in the middle, I'm gonna have above it 10 and below it 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this value is in the middle because it is having in the bottom 50% of my data, 10 above it and 10 below it, so it is 88. So that value would be my Q3. I could also, by the way, use here the same rule I had here. So instead of using just n/2 for the first half and n/2 for the second half, and even n/2 for the whole data set, if I'm talking about the Q2, I can use the location rule here. But let me postpone, and I would get the same answer. So we are gonna have an example that is in details using that rule. But just to give you an idea, how about going ahead and calculate Q1 using that rule? Q1 is the 25th percentile. So if I'm applying that rule, it would be what? It would be, okay, let me try to, it would be what? It would be L equal to 42 times 25, isn't it? Over 100. I'm again calculating the Q1 using the L location rule, and this should give me 10.5. So 10.5, it's not a whole number. I'm gonna raise it up. It's gonna give me 11, and this is again what we have here. So this is the same 11 here. So my Q1 would be 61. So I can also use the same rule like we have here, but this is another way to find Q2, Q1, and Q3, but still that rule for the percentile will apply here using the 25th position for Q1, 75 for Q3, and of course 54 Q2. Now the interquartile range IQR for short and outlier detection. The interquartile range is defined by the difference between Q3 and Q1. Okay, and this measured IQR is actually one of the measures for variation for the middle 50% of your data. So after all, IQR is one of the variability measures that is specifically reflecting the variability inside the middle 50 of your data. So I can calculate that one, and it would be handy to graph the box plot as we will see on our coming or remaining slides. But how can we use the interquartile to detect the outlier? So mathematically, outliers can be determined by the following rules. If an observation was greater than Q3, your third quartile, plus 1.5 times interquartile range, then it would be considered an outlier. And if it is, or if it is less than or equal to the first quartile minus 1.5 interquartile range, then it would be considered an outlier. So these two boundaries are reflecting the limits for an observation to be an outlier. And if we found out that we had outliers in our data set, then as we did discuss before, the median would be my best central tendency measure in this case, if you have been asked to calculate one of the central tendency measures. So do not use the mean in these cases if you did figure out that you have outliers in your data set. So next we are gonna talk about 5-number summary, which each data set can have, or you can calculate it for each data set. You can find the minimum, maximum, and Q1, Q2, and Q3. These 5 numbers are called 5-number summary statistics, or 5-number summary for short, and these are summarizing the whole data set. And I can use these 5 to create what is known by the box plot. So the box plot, it's gonna begin with the minimum value and end at the maximum value in general. And in between the minimum value and the maximum value, we are gonna put a box. That box will begin at Q1 and end at Q3, while between Q1 line and the Q3 line, we will have the median, which is the Q2. and that one is the whisker. The left whisker is beginning at the minimum, while the right whisker is beginning at the maximum. That box plot could tell us or summarize for us even the shape of the distribution. How? Well, we do have two rules here, one for the median rule of thumb and one for the whiskers rule of thumb. For the median rule of thumb, if that line was somehow or approximately in the middle of the box, so exactly in the middle or roughly in the middle of the box, or in the middle of the distance between Q1 and Q3, and that distance, as we said before, representing the interquartile range. So the distance here, the length of that box is equal to the interquartile range, Q3 minus Q1. So if Q2 was exactly in the middle of that distance, then the whole distribution would be roughly symmetric. But if Q2 was closer to Q1, then in that case, we are gonna say that the distribution is right skewed or positively skewed. If Q2 was closer to Q3, like that line, when you graph it at the value of Q2, you would find out that it is more closer to Q3 than Q1, then your distribution would be negatively skewed or left skewed. So these are the three rules for the position of that line in your box. The rule of thumb for the whiskers is saying that if these two whiskers were roughly of the same length, then you would have a symmetric or almost symmetric distribution. However, if one of them is lengthier than the other, then the distribution is shifted towards that lengthier one. So if the left whisker was lengthier than the right one, then your distribution is skewed to the left. On the other hand, if the whisker was lengthier in that direction, the whisker, the right whisker, then your distribution is skewed to right. Usually these rules, the median and the whiskers rules, are going in the same direction, but sometimes they are not. Well, rare times. In these cases, the whisker rules is talking about the whole distribution, while the median rules is focusing on the middle 50 of the data, exactly the data between Q1 and Q3. So a box plot with outliers, which we are gonna call modified box plot. Now, when outliers exist, we need to modify our box plot somehow to reflect these outliers. How? Well, the length of the whisker in the direction of that outlier would be somehow modified. So how? Well, this is what we are gonna see. If an outlier was in the direction of the right whisker, then we would extend the right whisker only to the largest value within 1.5 times the interquartile range from Q3. On the other hand, if you did have an outlier in the left direction, the smaller values, then you would extend the left whisker only to the minimum value within, again, 1.5 interquartile range from Q1. So if this is our box, and this is the mean, median, and Q3, and of course the length of our box is the interquartile range, so I would create the 1.5 times interquartile range from Q1 to get the lower boundary of identifying or detection of the outlier, and I also will calculate the 1.5 times interquartile range from Q3, the upper boundary for outliers, and I would say, okay, any observations that will appear beyond these two lines would be considered an outlier. So if I have these two dots, these two values, dots, instead of extending my whisker to the minimum value. This is the minimum value in that case, but because it is beyond the 1.5 interquartile range from Q1, these are not gonna be put on the whisker. We are not gonna extend the whisker till here. We are gonna just stop the whisker to the minimum value of my data that is within that boundary. So it's not gonna extend beyond that boundary, which is 1.5 interquartile range from Q1. So any observations that will appear here would be an outlier, and the length of your whisker is gonna be modified. While here, if any observation would have appeared here, it would be declared as an outlier. In this scheme or in this sketch of my box plot, I didn't have here any outlier. So the maximum, that one, is the true maximum. This was the maximum value I have in that case, while these two were the minimum one, but because they did appear beyond that lower boundary of my outlier detection rule, then I would not extend my whisker to the smallest one. I would just stop at the minimum one inside that range. So let us see that in an example. We have here example 4, traffic violations for 10 days. So we have here 10 values of traffic violations, and we need to find to graph our box plot. So to graph it, we need to find the minimum value, maximum value, minimum value, maximum value, Q1 and Q2 and Q3. So we need to identify all of our quartiles, minimum and maximum value. This is the minimum and this is the maximum, and we need to decide whether we do have outliers or not, so that we are gonna have a modified box plot or a regular box plot. So let we do that. So L for the median would be what? It would be this. These are 10. So 10 times 50 over 100. It's gonna be what? It's gonna 10 times 50. It's gonna be 500 or so. The fifth position, 1, 2, 3, 4, 5, and this is again a whole number, so I'm gonna average these two together to get the median. So the median would be the average of these two. No, we need it. So this is the rule. Okay, we have it here, 5, and it is a whole number, so I'm gonna average the two values in the fifth and the following position. So the fifth and the sixth position, average of that would be 18.5, and for the Q1 it's gonna be again 25 times 100 times 10 over 100 is gonna be 2.5. This is not a whole number, so we are gonna just round it up, and it's gonna give me a position of 3. So that observation in my arranged array in position 3 would be my Q1. Okay, oops, here is my Q1. And for L3, the third quartile, again 75 is the rank of my Q3, which is the 75th percentile, times 10. 10 is again how many data do we have over the 100. It's gonna give me 7.5, and this is not a whole number, so we're gonna round it up to 8, which means our Q3 is 22. Now the interquartile range is the difference between 22 and the 15, which is 7, and this is a measure of the variability in the middle 50 of my data. So the lower boundary for outliers, which is there any observation beyond 1.5 interquartile range from the Q1? So Q1 minus 1.5 times interquartile range would be 4.5. So this is the lower boundary for any observation to be beyond which any observation would be considered an outlier. Here we don't have any observation beyond 4.5, so we don't have an outlier in that direction. Let's check the higher direction, the upper boundary, which is 22 Q3 within 1.5 interquartile range. Again, so 1.5 times the 7, 1.5 interquartile range. This would give us 32.5. And in our data set, the highest value was 25, so we don't have any outliers. So no outliers here. I can just go ahead and graph my box plot very easily without any outlier, which would extend from the smallest observation till the highest observation. From 9 to 25 my whiskers will be, and inside the box it would be exactly at the position of those values we have found. Now another example, 80. We do have how many observations here? We do have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We do have 10 observations, and we would like to construct here the box plot. So again, we need to find Q1 and Q3 and decide whether we do, and Q2 of course, and we would like to check whether we do have outliers or not. So let we arrange again, because we are dealing with measures of positions, to find Q1 and Q3 and Q2. So this is the arranged array of our data, 10 values arranged from smallest, the minimum value, to the highest one. And Q2 would be 83.5. How? Well, again, it's 10 over 100 times 50, it's gonna be 5. So 1, 2, 3, 4, 5. And I need to average these two together. So adding these together and dividing over 2, it's gonna give me 83.5. For the Q1, it's 47. Why? Because again, let me write it just to remind you again. For that one, I would have, it's L, the L for the Q1, let me write it like that. Okay, it's again the 25 times the 10, which is my N, 10 observation, over 100. Okay, this will give me again the 20 or 2.5. So raise it up or round it up, it's gonna be 3. So the value in position 3 would be your Q1. So this is your Q1. And similarly for the Q3, it's gonna be 7.5. So in position 8, it's gonna be your Q1 in Q3. So I have first quartile, second, which is the median, and the third one. And now interquartile range. The interquartile range is the difference between Q3 and Q1. So it's 117. And I can now check whether I do have outliers or not, as we would like to check here, find the outliers or check for any outlier. So we will put the lower boundary within 1.5 interquartile range from Q1 and the upper boundary within 1.5 interquartile range from the Q3. Lower boundary again, 47 minus 1.5 interquartile range, it's minus 126.5. So any observations that is below that negative value would be considered an outlier in the small direction, in the left tail, or in the left values. So the smallest one was 30, so we don't have outliers in that direction. We don't have here any outlier. So bingo, this, my left whisker would be extended to 30. And upper boundary, well, 164 plus 1.5 interquartile range is 339.5. Any observation again above that value is gonna be considered an outlier, but we have here the maximum is that one. So we don't have any outlier from these two. We don't have any outliers in that direction. So we can go ahead and graph our box plot. So let me just put it like that before heading to the other slide. Okay, this is 8164. Okay, and I'm gonna extend that till the maximum value, which is gonna be 296, while the median would be somewhere here. Okay, this should be, of course, when you graph it on your paper, it should be like using not a sketch like that, but a nice scale, chosen scale. And this is 47. Okay, and here I would extend my whisker till my smallest value. So we don't have a modified box plot. This is a usual box plot. And we don't have any outliers. So since I don't have here, I just sketched it, I cannot talk about the shape, but let us see our app. We have the app 3, so let we use the app 3. So let's use the app 3, our R app, to graph this box plot to scale instead of a sketch. So how to get that app? Either directly through that link, or I can go to that website first and this page inside that website and go ahead and hit app 3 on this page, and it will open for me that page. Here it's allowing me to either enter a single group data or to upload for two group an Excel file, as we will see in our coming example. So it's a single group. I have only one data set, so I entered my data, my previous data, and this is the graph for it. As you see, we don't have any outliers, no red dots, so no rebels here, no outliers, so I'm fine. No outliers. And now let us check our data. This is the minimum, which is here 30. Q1 is 47. This is 47. And the minimum was 30. And this is Q2, which is the 80. Was it 80? Yeah, 83.5. And that one, Q3, which is the 164. And the maximum value was my 296, and the mean was the 1114. So the mean is here. Okay, the mean is here with a value of 1114. And we did discuss before, if the mean is greater than the median, then we have positive skewed distribution. So to answer this question, is it symmetric or not? Actually, it's not symmetric. It's skewed to right, which is positive. So positive skewed is right skewed. So these are the same. And since it is right skewed, so we need the best central tendency measure should be the median. Again, according to our two rule of thumbs, the one of the whiskers, we have here a lens here, right whisker. So again, this emphasizes I do have a positive skewed distribution, and according to the median rule of thumb, I have Q2, the median is closer to Q1 than it is closer to Q3. So again, it's right skewed distribution. Do we have next? Yeah, we do have another example for two groups. So data represents the number of hours that 12 part-time employees at a toy store worked during the weeks before and after Christmas. So we have 12 data points for each before and after scenario. and we want a box plot. So I could have, go ahead and you can do that also. Go ahead and calculate Q1, Q2, Q3 minimum and maximum for each group and compare the box plots. But let we see that using our app3 again. So again, I am activating or using the app3 from our last slide. And instead of using here the single group, I'm gonna use two groups, and I did prepare a C comma separated value Excel file where in the first columns I have listed all of my data and labeled that column by values, small letters. And the second column, I named it or labeled it group, again small letters because the file is case sensitive, and I would write in that second column where each data come from. So for the first data, if I'm listing before first, then the first 12 data are gonna have the same value before in that second column, while the last 12 data they are gonna have after in the second column. And once I did upload it, this box plot gonna be created, and as you see here, which one is having the high spread, so interquartile range is from here to here. That box is having the highest interquartile range, and also from the box plot you can read, by the way, the range, because the range is maximum minus minimum, so it is having also the highest range. So this distribution is having more spread, so this distribution is having more variability in it. Now looking at the Q1 and Q2 and Q3 and saying something about the distribution shape, since we do have here the left whisker is lengthier than the right whisker, so this is negatively skewed or left skewed. So the first one is having more spread, so the before hours more spread, so the before hour in terms again of is more in terms of interquartile range, because the length of that box is higher than the second box, and also in terms of the range, maximum minus minimum, it's higher than the maximum minus minimum in that after distribution. So the working hours before Christmas is having more variability in it, and it was less skewed. However, for the other distribution, the other group after Christmas, it is positive skewed. Why again positive skewed? Because the right whisker is lengthier than the left one, and again positive means right skewed, negative means left skewed. And this is in terms of the whisker itself, the whisker rule of thumb. And if you are using the median rule of thumb, here again Q2, this is my Q2, is closer to my Q3, so it means I do have a left skewed distribution, while here I have the opposite, the Q2 is closer, the Q2 value here, see its value is closer to the Q1. So I have here this in terms of the median rule, it's also saying I do have a positive skewed distribution, so more spread here. And even the whole distribution for the after, like the Q3 of the after group after working the working hours after Christmas, the Q3 of it is almost, as you might see here, is almost like the Q1 of the before Christmas. So it seems that before Christmas they are working more than after Christmas. So So the whole distribution here, 75% of the working hours after Christmas is less or is equal to the 25% of the distribution for the before Christmas. And if you want to know the exact value, the app will give you the exact value as we will see on our coming slide. So, and here are, as I said, the data values for my two groups. Minimum value for the after was 12, while the highest one was 32, while for the before, the minimum value was 12 and the highest value was 38. So this is what we had on our previous slide. And the median values, as you see, 18 hours, only 50% of my 12 workers worked less than 18 hours in the after Christmas case, while 50% of my workers worked below 30 hours in the before Christmas group. And what else we can say here, I can talk about the mean. The mean here, the mean of the working hour for the after Christmas group was 18, roughly 19. It's close to the 18, while here it was about 27, so a little bit less than the 30, which means it is here negatively skewed, while here it's a little bit positively skewed, as we did see in our graph. And because it's skewed and not symmetric, the best central tendency measure in this case would be again the median here and the median here. And this is the end of our lecture. Please go ahead and use the app 3 with your own data set, or even with the same data set we had in this lecture, and see you next lecture.